Hi, welcome all. I'm Ajay Bhosle and welcome to All About Engineering YouTube channel. So actually we proposed new idea to start the flyback converter design and analysis of it. So different lectures are available on this channel. So kindly if you want to learn, then kindly follow this channel and its lecture. Okay. So while going through this different lecture series, first I want to tell you that while making this video, I'm assuming that the candidates that have some basic knowledge about the forward flyback converters and all the things like switches and losses and all the things. Okay, supposedly if any new candidate is over here, then that candidate has to comment over here, means actually which topic you want to know in depth. So definitely we'll try to make it. So now before moving towards the flyback converter design and analysis, I will elaborate some advantages and disadvantages of the flyback converter. Okay, so without wasting time, we'll go through it. So basically, first advantage of flyback converter is the simple design, right? And second one is actually if you are comparing flyback converter with a forward converter, then definitely flyback converter have flyback converter don't have inductor as compared to forward converter. And the third advantage is basically multiple outputs we can able to get from the single input. Actually this advantage is also is available in a forward converter also, right? So and the one big disadvantage for the flyback converter is like that we are able to, means you can design, if you are capable to design flyback converter more than 100 watt, then you can, but the thumb rule is like that generally we are used to we are using flyback converter up to 100 kilowatt, right? So before moving towards the in-depth analysis of flyback converter, first I will elaborate the some simple waveform of PWM converter and how we are going to calculate the average value as respect to your turn on time and like that stuff. Okay, so as shown in picture, this is your PWM converter output waveform. Means as you know that PWM have two waveform. Means if you are generating the PWM signal, then definitely that has to PWM has two waveform, like the reference waveform and a carrier waveform, right? So you are comparing the reference and carrier waveforms, and after that you are going to generate this square waveform. Okay, right? I think many of candidate has seen this kind of PWM waveform, right? This is actually this waveform, means whatever I have shown you over here, that waveform is also generated from the carrier and reference signal comparison. In the practical circuit, while comparing, you are using comparator, op-amp, like this stuff for the comparison. Okay, at last while design at last of design phase, we'll look over through that also. So now just focus on this waveform. Okay, actually why I'm going to explain, because this mathematical analysis which we are going to use in Holt second equation for deriving your transfer function, there we are going to analyze, and in control loop analysis of the flyback converter also I'm going to use this mathematical stuff. So please kindly pay attention on this one, right? So this is a total waveform is divided into two sections, that is a T0 to T on. This is the first section and this is the second section. This is turn on section and this is turn off section. So total time span for this waveform is a TP minus T0, that is a T0 means 0. At T is equal to 0, this waveform is starting, right? So this is your this is nothing but we are going to find out the integral of this waveform. This is the total integral formula for this waveform. This is TP is nothing but your total time period for waveform. In this waveform it is a TP, right? So 1 divided by TP, integral of 0 to TP means total time period, right? And VT is nothing but your signal. Okay, means supposedly for this example I calculated a signal as a VT. This is a VT waveform, right? So we have to integrate total signal over here, right? So as I explained, this is the integral of first section and this is integral of second section, right? So over here this is a turn on time period, that is 1 divided by TP, 0 to T on, and this is a T on to TP, means T on to TP, right? Over here you are able to understand the amplitude for this waveform is a 0, right? Actually this is a baseline, right? What I am drawing here, and this is your average value. So what I want to explain here, as respect to your waveform length, you are going to change your average value amplitude. That is the point. right? So if I'm making this change over in a length, means the length means turn on time, then my average value magnitude is going to shift in this direction. Okay, so right, this actually I want to explain over here, right? So if means you are increasing turn on time, then definitely average value is going to shift upward. If you are decreasing turn on time, then your average value is going to shift downward, right? So this integral is nothing but your area. Okay, so this is a turn on area, right? This total is a turn on area. So area, total area, this is your total time period, which comes from this integral formula. Okay, 1 divided by TP, and this is the area. Area means what? This is nothing but your rectangle. Rectangle area means width into height. So right, so here I explain this one. This is your height, V peak. Okay, right, this is your peak value. This is your peak value, right? Just focus on this one. And this is your turn on. This is your width into your height, that is a T on into V peak divided by TP, right? And for this section, okay, this is second section. For this, V peak is a 0, that's why we are total value is getting to tends to 0, right? So this is only in this total waveform period, this is only turn on time period, right? So this T on divided by TP is nothing but your duty. Duty means how much time you are going to turn on your waveform, right? That is the duty. So duty into V peak. So V average value is nothing but V average value, right? V average value is nothing but your duty into V peak, right? So now we'll move towards the next section, right? This one. So over here I just I want to give some glimpse about your waveform, right? This whatever I explained before, the square waveform, this waveform is nothing but that only. So now what I am going to, first I created the PW waveform. At after some lectures I am going to explain you the closed loop structure of a flyback. Over there I will explain how we are comparing this waveform and how we are generating PWM. Just for sake of purpose, just now understood that from PWM converter we are able to get this square waveform structure like so. And this square waveform structure we are going to fit to our switching devices. So for this example, means for flyback I am going to consider a MOSFET, right? So why I am going to consider MOSFET, like this stuff we will explain in the next lecture, so kindly tune with us, right? So for just understanding purpose, just now just remember we are going to use a MOSFET, right? So this is a turn on time period, this is a turn off time period. And what is the formula for frequency? Frequency is nothing but inverse of your time period. So time period is inverse of your frequency. This is vice versa. So this is a turn on time period. Okay, D into TP, D into TP. This is turn on, and this is turn on type, turn off time period. Turn off means this area you have to find out, right? This value. So TP minus your DTP means TP total time period minus your turn on time period DTP. So what is the formula? Now you are going to take it out, TP common. Okay, so TP 1 minus DP, so that is D dash. D dash means your turn off time period. So duty is equal to turn on divided by T off. Okay, right. So now we'll move forward. So duty is a turn on time period of MOSFET and total time period, right? So actually while moving towards the next point, first we are going to calculate what is the difference between the flyback and the forward converter. So one point that is actually important, first we have to focus on this point. This is a flyback means the whatever inductor we are going to use in a flyback, okay, that have some differences with your forward converter. The inductor which we are going to use in flyback, that is going to store the energy in the magnetic form, right? As you know that the basic of the inductor and capacitor, inductor is going to store energy into magnetic form, and your capacitor is going to store energy into static form. So over here we are going to store a total energy, whatever it is coming from the source, that is going to store in the magnetic form. Okay, so the inductor which we are used in the flyback, that inductor is able to store the energy in a magnetic form. This is the one bold and most important statement. And for the forward converter, the inductor which we are going to use, that is not going to store the energy, right? Mark it out, this statement, or note it down in your notepad, right? So This only actually I elaborated over the store energy during the turn on time period. In this time period MOSFET is on. Okay, so basically I want to give some glimpse about the network theory. As you know that many of us are actually going through the transient analysis in our BTech period. Okay, right. So over there what we are doing, one switch is there, and for inductor the energy is like that, means for the, if I'm turning on or off, means I'm making some changes in a switch at a t0 period. Okay, here I will note it. This is a switch. It is a switching action which is going to happen at t is equal to 0 period. Okay, and previously before this one, this is a t is equal to 0 minus period and t is equal to 0 plus period. Okay, so for inductor, whatever current in a t0 is going to replicate in the t0 plus. Right, this concept actually is most useful in this flyback converter to analyze how inductor is going to store the energy. Okay, we'll go through that one also. So this is statement: energy stored in the flyback converter during the turn on time and energy is released to the capacitor and resistor during the turn off time. Okay, so now we'll move towards the circuit and its analysis of the flyback converter, right? The basic circuit. Okay, so now let it go. So magnetic flux form, whatever I told is that only written over here. So in the magnetic form it is going to show. So basic actually, so means as the title of our video is like the analysis and the design of EFC, means flyback converter. So first, while doing analysis, what actually procedure I have to follow, means supposedly one new basic candidate is over here, then that guy will think that, oh, actually analysis means what I have to do at a starting. So I will elaborate what things you have to consider while analyzing the flyback converter. So there are 4 steps. First, you have to draw the schematic of the flyback converter, right? Then you have to write the equations of that flyback converter. Then you have to draw the schematic for turn off. This is turn off, this is turn on, schematic for turn on, and then write the equation for the turn on. Then you have to go through the turn off, and for that you have to write the equation, right? Okay, so now just focus on this one, analysis part. So first I will try this. First I will elaborate the total single line diagram of your flyback converter. Okay, right. So flyback converter consists of the 3 components, right? So first component is your inductor, that is a coupled inductor. Then second one is your diode, third one is your capacitor, and first, so 3. This is nothing but your load side, this is nothing but your input side. So flyback mainly consists of your 3 parts only, 3 components only: inductor, diode, and capacitor. So these components only now going to play major role in the flyback operation, right? So one by one we'll focus on this component and its design and its analysis, how it is going to operate, right? So now stay tuned. And this, okay, right. So here just now you have to focus, right? So first what I will do, I will explain what is the turn on schematic of the flyback converter, and then I will elaborate what is the turn off schematic of the flyback converter, right? So for the turn on, my switch is going to be in a short circuit condition, and for the turn off, my switch is going to operate in the open circuit condition. So this is a off condition and this is a on condition for my flyback. So this is a voltage, V in voltage. This is nothing but the DC voltage, and this is your coupled inductor. And over here you have to note this point: for the flyback converter, the polarity, means dot convention of the 2 windings is exactly opposite, right? This is most important. Okay, over here dot means what I am assuming over here, dot means my current is going to enter into this point of the inductor. Okay, right? So like this for turn on procedure and turn off also. So right, so first we'll take overview. So at the first time my switch is going to be in short circuit, so total my DC energy is going to store, means is going to flow, means current is going to flow through the primary winding. Okay, now what happened, suppose I am assuming this is a positive, this is a negative. Okay, so exact this is opposite, so dot means positive, whatever over here dot, and this is a negative. So the at this place, what I explained over here in previous diagram. Okay, this is diode over here. So for turning on the diode, anode should be positive and cathode should be negative. If if diode means positive means negative means it is not like that. Okay, diode should be positive. The anode potential, note it down, anode potential should be greater than cathode potential. Okay, actually at the time of BTech what I am considering that anode should be positive and cathode should be negative. It is not like that. Anode potential should be higher than your cathode potential. Suppose I am giving example. Suppose my cathode potential is a 2 volt positive, right guys, 2 volt positive, and my anode voltage is a 1 volt. What it means? The voltage difference means anode have lower voltage. Suppose now in second case I am making as a anode voltage as a 5 volt positive. So now at this case diode is going to turn on, right? So this only I want to elaborate, means see, this only I want to convey that anode potential, the potential word is some potential word that you have to focus on, right? I think hope it is clear. If someone is facing still have some confusion, that then he or she is able to, I mean he or she can put some comments. So if it is not understandable, then we'll follow some comment over here, right? So I think this lecture is not now going to exceed some time. So in next lecture I will elaborate this circuit and analysis part. So guys, whatever I explained, if you are not able to understand, just comment it out. So we'll make some improvement in teaching style or something like. If voice is not clear, then that also you can comment it out. So our team will work on it. So take care, be happy, and learn something, right? So bye.